Hello everyone. Welcome to a new chapter of our 2511 course. So, in this chapter, we are going to talk about mathematical induction, that is our chapter 5 in our textbook. So, what is a mathematical induction? Mathematical induction is a way to prove a mathematical statement. Okay. So there are a couple of basic elements in the mathematical induction, and we're going to see a couple of examples. That means how we can prove a mathematical statement using mathematical induction. All right. So before that, I want to use an example like what is actually a mathematical induction. So we can visualize the mathematical induction just like a ladder. Okay. So let's say we have a ladder and we have like infinite number of steps. Okay. All right. And even though we have infinite number of steps, we have some first step. We have actually one initial step. So let's say that's your initial step, means the first step. Okay. All right. Now it's a ladder and it had a lot of other steps. Okay. Now I want to ask you, can I go to some nth step using this ladder? Okay, or in the last step, if you know how many step in this ladder, let's say I'm asking you, can you go to the last step or some given step in this ladder? So if I want to go to a given step like the last step, so all I have to do, the first step has to be I have to try the first step. Okay, I have to be able to take the first step. Okay, now if I can able to take the first step, probably I can take the second step. Now if I can take the second step, I can take the third step. Okay, now if I can take the third step, I can take the fourth one. Now looks like if I take the first step and from one step, if I can go to the next step, I will be able to go to the any step from this ladder. Okay, it could be the last step or it could be a given it could be some given step or it could be the last step. Okay, so all I need here, I have to be able to take the first step. Okay, and like if I'm at any step, like at step k, now if I'm at any step, can I go to the next step? Okay, like if I am at step k, can I go to step k plus 1? All right, so that's two things. Okay, that's two things here actually important. And if I can say that I can take the first step, and being at any step, I can also take the next step using the last step. Like if I'm at the first step, I can take the second step. If I'm at the second step, I can take the third step. All right, so that means if I'm at a step k, I can go to the step k plus 1. Okay, then I can say that yes, I can go to any step in the ladder. Okay, I can be at the any step in this ladder. All right, so a mathematical induction is actually use the same concept. Okay, so using the mathematical induction, we are going to prove a propositional function or a mathematical statement. Okay, as you can see that it's p of n, it's like a propositional function. All right, and I can prove a propositional function using mathematical induction, and here I am going to use the same idea, same concept. So a mathematical induction has 4 basic elements. All right, so we are going to first prove that our propositional function is true for some fixed value n naught belongs to integer number. So here n naught has to be belongs to integer number, and n naught is our, like it is known as the base case. All right, and n naught is actually our basic step, our first step. Okay, for example, in this example, in that ladder, if I want to go to any of the step, I have to take the first step. Okay, so the first step, so taking the first step is our base case. Okay, so the first step, I mean, we have to have a base case and we have to prove that our propositional function is true for some for some base case. Okay, for some fixed value n naught greater than n naught belongs to z, some positive integer. So that will be our base case, and then there is going to be another step known as inductive step. Okay, so in the inductive step there are also two things. One is the hypothesis and another is the induction. So hypothesis says that we are going to assume that I can be here any step like k. Okay, if I am at any step at k, then using the step k I can be in the step k plus 1, means I can go to the next step. All right, so in this case we are going to assume that pk, our propositional function, is true for some value k which is greater than our first value, first case n naught. All right, so you can see that we are here assuming, means that's actually our hypothesis. Okay, hypothesis means we are going to assume something is true, then we are going to take the inductive step. So using the hypothesis we are going to prove that if pk is true, then pk plus 1 is true. Okay, so we're going to prove that if pk is true, and we're going to assume that. So that's why this is our hypothesis. Okay, and we are going to prove that if pk is true, then pk plus 1 is also true. All right, so that's our induction. Okay, and the base case is that we are going to first we are going to prove that pn naught is true for some base value. Okay, where n naught is actually the first step, n naught is going to be the first step. Okay, so and each of the value here, n naught, k and k plus 1, everything is going to belong to some integer number. All right, so the final step is the conclusion. Now I know that I can take the first step, and being at any step I can also take the next step. That means actually I can go to the any step in this ladder. So let's say I want to prove that I can go to the last step of the ladder. So that means I can prove proving this first two condition. Okay, so my final step is the conclusion. Okay, so conclusion is that we can conclude that Pn is true for every n. All right, every value of n which is greater than our first step. Okay, n naught. All right, so let's see one example and that will be very clear. So we are going to prove that for any natural number n greater than or equal to 1, we're going to prove that the summation of 1 to any number n equals to n times n plus 1 by 2. Okay, so it's actually the same thing like writing I equals to 1 to n, I equals to n times n plus 1 by 2. All right, and when we are going to prove like something like that, we have to make it clear what is our propositional function, what is our base case, and what is our hypothesis. Okay, means hypothesis in our inductive step. So here what actually we are going to prove, we are going to prove any propositional function. So in this case our propositional function will be, let Pn be 1 plus 2 plus 3 equals to n times n plus 1 by 2. So that's the propositional function we are going to prove. So you can see that actually what we are trying to prove is the summation of summation of number 1 to n is same as n times n plus 1 by 2. All right. So all the number here, like n0, n1, n2 to n, okay, all the number, and the number starts from 1. All right. So in this example, our base case, we are going to prove n with n0 value 1. Okay, means what is the value of p1? So the value of n0, okay, the value of n0, you can someone read it like n0 or someone read it like n0. Okay, so the value of n0 depends on actually our propositional function. So generally we take the least item, all right, the smallest item, all right, the smallest item from our propositional function. So here we are trying to prove that the summation of the numbers from 1 to n is n times n plus 1 by 2, and all other numbers are actually positive integer number. So here the smallest item here is 1. So that's why we are going to use 1 as the first item, all right, and our base case, we are going to prove that p1 is true. All right, so let me write down the base case. All right, base case, we are going to prove p1 is true. So you can see that p1 means what? p1, it means actually from 1 to 1, right? So if this is our p1 is going to be just only one number. So p1 will be 1 equals to n is 1, so 1 times 1 plus 1 by 2. Okay, so here it's actually very easy step, because all we are going to do, we are going to just plug the number, okay, plug the value of n into our propositional function. And here we can see that we have our left hand side 1, and in our right hand side also we have we can see that here we have 2 by 2 equals to 1. So we can prove that, I mean it's proved that p1 is true. Okay, so p1 is here, we have 1 equals to 1 times 1 plus 1 by 2. All we are doing, just plug in the number, okay, in our propositional function. All right, so which is 2 by 2 and 1. So that's proved. Okay, so the base case is proved. Now our induction step. So in induction step, first we are going to talk about the hypothesis. So hypothesis says that we are going to assume that pk is true. Okay, so if pk is true, that means now our n value is k. So here also we are going to plug in just the value k instead of n. So if pk is true, that means pk is actually like 1 plus 2 to any value until k, and this value is going to be same as k times k plus 1 by 2. So hypothesis means we are assuming pk is true. All right, now having this hypothesis, we are going to prove that. Okay, that's our second step of induction. Okay, we are going to prove that pk plus 1 is true. Okay, so we're going to prove that pk plus 1 is true. Now pk is true. All right, so I'm going to just write it down here. Let's hope I'm going to find enough space here. So I'm just write down the pk, k times k plus 1 by 2. Now if pk is true, pk plus 1 is going to be actually just, I'm going to add k plus 1 with this pk, right? So this is going to be k plus k plus 1, and I'm going to add k plus 1 in both side, right? So k divided by 2 plus k plus 1. All right, and I'm going to actually use the next page. All right, so I have 1 plus 2 plus 3 plus k equals to k times k plus 1 by 2, which is my pk. Okay, that's my hypothesis. And what actually I'm going to do, I'm going to add k plus 1 in both sides. So that will be k times k plus 1 divided by 2 plus k plus 1. So now let's just do some calculation. It is going to be 2 times k plus 1 by 2. All right, so this is same as writing like k plus 1 times k plus 2 by 2. So you can see that actually here I am using the distributive rule, right? So here you have k plus 2, you can distribute k here and you can distribute 2 here, so you will find this thing. All right, so now what is that? Okay, what is this value? So this is actually same for k plus 1, right? So if I have k plus 1 is true, all right, so this is going to look, pk plus 1 is going to look exactly like that. Pk plus 1 is going to look exactly from 1 plus 2 plus until k plus 1, all right, equals to, now n value is k plus 1, so k plus 1 times k plus 1 times 1, which is k plus 2 divided by 2. So that's my pk plus 1. So if pk equals to true, I can prove that pk plus 1 is also true. So that's my induction step. Okay, and that's actually 2 and 3, right? So the step 2 is the hypothesis, which we are assuming pk is true, and having pk is true, we are going to prove that pk plus 1 is true. Now the conclusion is, so the first last step is conclusion, and we can say that for all n, okay, where n greater than or equal to 1, we can say that Pn is true. Okay, all right, so in this example we are going to prove that the sum of first odd integers is n square. So that's actually in your book segment, that is 5.1 problem 3. Okay, all right, so I'm going to use actually the whole of the page. All right, so as we said that we are going to use all the step for mathematical induction. So the first step is the basic step, all right, and the second step, and in the second step we are going to prove the induction. Now before that, actually the first thing is that we have to be clear about our propositional function. What actually we are trying to prove? It is saying that the sum of first odd integer is n square. Okay, so what does it look like? The first n odd integer, so the first one odd integer is only 1. So the first two odd integer, like 1 plus 3, okay, so the first 3 odd integer, so if n equals to 1, this is like that. If n equals to 2, so the summation looks like this, 1 plus 2. And if n equals to 3, the odd numbers we are going to add 1 plus 3 plus 5. And if n equals to 4, means the first 4 odd integer is going to be 1 plus 3 plus 5 plus 7. Okay, so given the n value, what is actually the range of our odd integer we are considering? Okay, so what is the integer value, the last integer value here? All right, so this is actually our we can generalize it as like that: 1 plus 3 plus 5 plus, so the first n on odd integer, the last integer value we are going to add, it will be twice n minus 1. So you can see that if n equals to 4, the last odd integer is 7. If n equals to 3, the last odd integer is 5. Okay, so it is actually very clear first to show what is actually we are trying to prove, what is our propositional function. So here our propositional function we are trying to prove is that let Pn be 1 plus 3 plus, as we are saying that the first odd integer, it will be like until twice n minus 1, okay, equals to n square. So that's what actually we are going to prove here. All right, so that's our propositional function that we are trying to prove. So let's find first our basis step. So in this basis step, that means actually the propositional function is saying that the sum of n odd integer. So the basis step will be the sum of one odd integer, the sum of first odd integer. Okay, and here the least value, we can see that least value is 1. Okay, so we are going to prove that P1 is true. Okay, and what is our P1? So for P1, our odd integer value is going to be 2 times 1 minus 1, which is 1. Okay, so for P1 it will be 1, that will be our last odd integer. Okay, so and in right hand side we have 1 square. All right, so that prove our basis step. Okay, so we found our left hand side is same as right hand side though, so that that is actually our that proved our basis step. So now we are going to talk about inductive step. So in this step we need first we need a hypothesis. So we are going to assume that Pk is true. Okay, so here actually we are going to prove that, so try to actually write them or everything. Prove okay, so prove P1 is true. Now here in hypothesis we are going to assume that, so that's actually our assumption, Pk is true. So if Pk is true, then our propositional function is true, it like that, and it will look like that: 1 3 5. So all we have to do, we have to actually replace n with k, right? So it will look like twice k minus 1 equals to k square. So we are assuming that this statement, this propositional function is true. Okay, now we are going to prove that P k plus 1 is true. Okay, how I can do that? Let's give this equation a name. So we are going to add okay, now what actually we are going to add? So that's one thing we have to find out. So Pk is saying that the first k odd integer. Now Pk plus 1 is going to say that the first k plus 1 odd integer. Okay, and for the first k plus 1 odd integer, what is going to be our last integer value? Okay, and what is going to be this value? So first we have to find out it like that, twice k plus 1, all right, minus 1, and this will be twice k plus 2 minus 1. This will be actually twice k plus 1. And here actually you can see that what you can see that, so if twice k minus 1 is actually your odd integer. So the next odd integer will be, you are going to add 2 with that, right? So that will be twice k plus 1. So adding twice k plus 1 in both sides of 1. I hope you are getting all of my handwriting. So 1 plus 3 plus 5 plus, I'm going to just add this minus 1 plus twice equals to k square plus twice k plus 1. That's why I'm adding in both sides. Now what does that tell? That's also actually very easy. So that's same as writing k plus 1 whole square. Okay, so what does that tell? So this one is actually proving our pk plus 1, right? So if pk is true, we can actually show that pk plus 1 is also true. All right, so now how actually this is making a conclusion? We are saying that if p1 is true, okay, p1 proves that p2 will be true. Okay, so if p2 is true, p3 will be true. If p3 is true, p4 is true. Okay, and that's how it will, I can prove that it is true for any number n, all right, greater than or equal to n naught. Okay, and here n naught is actually our 1. So you can see that first odd integer, and generally we can say that n is greater than or equal to 1. So for any value n is greater than or equal to 1, we are trying to prove that. Okay, and here we can see that if p1 is true, using the inductive step I can say that p2 is true. If p2 is true, p3 is true. If this is true, this is true. All right, and that's how I can say that the whole propositional function is true for any value n which is greater than our first value n naught. Okay, greater than or equal to. All right, so that's our, actually I can say, make a conclusion. Then I can draw a conclusion that this is true for every n greater than or equal to n naught, and here our n naught is 1. Okay, all right, so this is problem 4 in our textbook. So I'm not going to actually show you all the step by step as I have shown you for the last 2 examples. So here the steps are all same. Here our n naught will be 1, and that's our propositional function Pn. Okay, so n, we have to first prove that this is true, Pn is true for n equals to 1. Then we have to prove that, we have to assume that pk is true, and if pk is true, can we prove that pk plus 1 is true? Okay, so first try to do it yourself, and then it is actually, it has already done in the textbook in problem 4. Then you can look at the textbook. All right.